Hello everyone, welcome to Munro Live. I'm Scott, and with me today I have the distinct pleasure of sharing the screen with Mr. Walker Lee, one of my absolute favorite people at this company. Walker, thank you for taking the time, buddy. Good stuff. All right, so we're gonna jump into it. What we have on the table today are the front and rear drive units from the Hyundai Ioniq 5. We're gonna step through some of the different kind of key elements. We'll talk at a high level. We'll summarize some of the neat features we saw, some of the cool manufacturing elements, what's different between the front and rear. Yeah, a lot of content to touch on, and just to upset Eric, we've left the plastic bags on all the components, so apologies in advance for that. But with that, so high level statistics first. Now these are the front and the rear units. They're not the same, but they are something that we've seen a few different vehicles on. This is Hyundai's E-GMP platform, right? So I guess what other vehicles have we seen, Walker, that had these same drive units on?
We've seen the Kia EV6 as well as the Ioniq 6, all of them featuring the same front drive units that are basically plug and play between all those vehicles.
Sure. And so I guess with any architecture, right, we'd expect to continue to see that as anything else, more Kias, more Hyundais. It makes sense from a volume perspective to try and reuse the same stuff and get some more of that volume. So I guess so far they've been one of the OEMs outside of Tesla that we've seen do this on more than one vehicle, and I guess 3 vehicles. So
yeah, exactly.
I definitely expect to see more of that.
Which one's the front?
That's the front, this is the rear. Okay, so now the Ioniq 5 that we had, it was an all-wheel drive variant, so it's got obviously 2 drive units. They do, though, I think we were talking about this earlier, they do have just a rear-wheel drive variant.
Just a rear-wheel drive, yeah.
Okay, so as far as the statistics, the type of motors, that type of thing, so these are both permanent magnet AC motors. They both have hairpin stators. They both have skewed permanent magnet rotors. They are oil-cooled, which we'll get into in a little bit, talk about the cooling strategies. And as far as an output, the rear is quite a bit more capable than the front at 168 kilowatts versus 74 kilowatts. And that, again, I think that's pretty consistent with what we've seen from other OEMs as well.
Yeah, the front's a little down on power, I would say, compared to some of the other OEMs that we've looked at, but overall it's pretty competitive and all sits within the same
sort of ratio from front to rear. Yeah, and yeah, if you're gonna have one motor that you have as your base vehicle configuration, it makes sense you'd have the larger one. They put that in the rear. So I guess this would be like a rear wheel drive architecture almost with an optional front that gets added in. But with that, one of the interesting things, so there's several interesting things to talk about here, but as we go through those, I think one important bit of context, Hyundai did develop these motors internally, right? So as we've talked about other OEMs and their strategies and what responsibilities OEMs typically choose to own, powertrain, at least historically, was a big one. And I know not everyone that we've looked at has used that. Sometimes they'll use off-the-shelf stuff from like a Bosch or a Magna or a Borg-Warner. These ones, they've got Kia, Hyundai all over them, right? This is...
And that seems to kind of be one of the people bringing things in-house, one of the things that OEMs are kind of trending to do for brought in-house. We saw Rivian start with a supplier, but now they've since brought it in-house. So it seems like a good first step into bringing some of the powertrain back in-house.
Yep, absolutely.
This episode of Munro Live is brought to you by Brilliant. Here at Munro, we love to get technical. Our engineers are lifelong learners and are constantly looking for opportunities to hone their skills, which is why we love Brilliant. Brilliant's mission is to inspire and develop people to achieve their goals in STEM. Brilliant knows that thousands of dollars spent on education isn't always attainable. So they offer courses in math, science, and technology for a fraction of the price in a format that allows you to learn on your own time. Whether you're interested in learning the basics to deepen your understanding while watching our teardowns, or you're looking to level up your skills at work, Brilliant customizes lessons to fit your needs, so you can learn at your own pace. With Brilliant's interactive approach, you can master large concepts in as little as 15 minutes per day. Here at Munro, our team's skills are more than just basic engineering. Adding on lessons in foundational logic helps improve problem-solving skills, which is essential for our lean design methodology. Whatever your goals are, you can get started on Brilliant right away with 30 days free. Plus, you can get 20% off your annual plan by visiting brilliant.org/MunroLive or by clicking the link below. Only the first 200 people will be able to claim this special deal, so act fast and get started on your customized learning path.
And with that, yeah, and we always certainly appreciate Kia, Hyundai. We'll put some links into this, but they've put out some really great information about their drive units. We're gonna pull some of the high points from that, but it's always great. I think we're also starting to see this trend where people are proud of their technology, right, and their patents, and they put some of it out there. So we'll drop in some B-roll that even maybe shows some of that when we talk about some of those technologies in a moment. But let's go ahead and we're going to move to the front here. The first thing we're going to talk about is the presence of a disconnect unit in this as part of this system. So again, we said this is the front drive unit here, and there's a pile of parts that comprise what's called a decoupler or a disconnect. That's basically going to be used to take. This is an offset gearbox, so you've got your rotor and stator are going to be on this axis back here. They're going to spin. You've got your stator here. The rotor's been pulled apart, but it'd be on this shaft. You're going to have a gear train that's supported with bearings. It's going to go to your final drive axis here. And on this final drive axis, you've got a electromechanical mechanism here. This is the housing for it. Goes on like that. But basically what lives in there is a worm screw driven decoupler ring. And we're going to show some of the components here. We'll show a picture of the full unit assembled as well. But you've got a sort of a selector fork that has a sliding gear ring that goes onto it. So this would be roughly located here. Then you're going to have a worm screw gear like this. So you've got that threaded portion that goes into here. There's an electric actuator that's going to drive this externally. So as we flip this here, you'll see that is splined. And we've got this actuator here that has a mating spline. That would go on there. And when this is electrically actuated, that spins, and that's going to cause this selector fork to move laterally, either in or out. And then in principle, what that's going to do, there's a section on the output shaft here that goes to the half shafts and to the wheels that there's a section that's splined that meets up with this, and there's a section that has basically nothing on it. And so whether this is moved left or right is going to dictate whether or not that driven set of wheels can freewheel without being coupled to the rotor and stator. And now I know kind of walking through that was a lot to explain, but essentially I guess to bring it back, a decoupler, why would someone even want that in an electric motor?
Sure, so Hyundai, like you said, have actually posted a lot of public information about some of these unique technologies. And so one of the things that they've already mentioned that this gives them is roughly 6 to 8% efficiency gain or range gain. They roughly equate to the same thing. So we did some math.
Yeah, this is good. I'm excited for you to walk through this. But yeah, so in a permanent magnet motor, you have this phenomenon called back electromotive forces or back EMF, where you could use it productively for regen, right? When you're winding down, it's working like an electric generator and putting power back to the battery. But if in an all-wheel drive application, if you're driving one set, in theory, the other motor is kind of pushing back against it slightly, and that back EMF at highway speeds, or if you're cruising, or if you want to maximize range and efficiency, you can envision a scenario where you might not want to have that drag on the system.
And decouplers haven't just been for electric vehicles, right? We see them in trucks. They disconnect the front axle, so there's overall just drivetrain losses from having to just move the physical mechanical components. But of course, it's kind of exaggerated in an electric vehicle, especially a permanent magnet electric vehicle. So, but if we wanted to equate this to kind of whether this is a net savings to the vehicle or what they're gaining with this 6 to 8%.
Yeah, walk us through it.
We did some rough math. There's a lot of assumptions here, but at a high level, the Ioniq 5 that we were looking at was an extended range 77.4 kilowatt hour battery pack vehicle, which gave it 303 miles of range. With the decoupler, this was their total mileage they had. So what would happen if we remove that decoupler? We're looking at, on the low end, if they get the 6% efficiency by implementing this, that would equate to roughly 18 miles of range. So without that decoupler, they would be sitting at around 285 total miles. So if, say, they were sitting at 285 miles and they want to boost this to over 300 miles of range, they really
that's like kind of a threshold.
Yeah, everyone's kind of for the window
nice
sticker.
Number,
it's a nice 300 mile range number. But
yeah.
So if you wanted to get to that 300 mile range number, they really had two options to go with here. The first one, which they chose to go with, was using this decoupler that it varies, the implementation. This compared to Rivian is very different, but call it a $100 component or somewhere around there to get
Plus
to
or
that.
minus. If you want the exact cost, we'd be glad to sell you a
Sure.
report, but something in the order of 100, let's say, for the mechanical elements that comprise that decoupler system.
Yeah, and that boosts them over to just over 303 miles. The other
Alternative
option
too,
would be if you just wanted to add that capacity in form of kilowatt hours or additional cells to get that 18 miles. So we did some math, but overall what they would need to add to get 18 miles is about 4.8 kilowatt hours to the overall pack, which would equate to roughly 24 cells. But just going at an average dollar per kilowatt hour, 125 is a fairly safe number to go with. So 4.8 kilowatt hours would equate to roughly $600 worth of cells they would have to add to get to 303 miles. So you're looking at a $500 delta to the net vehicle. So it's a really good example of probably doing the right thing for the vehicle and not necessarily just the system, because it certainly adds cost and complexity to the EDM itself, but at a vehicle level, it could lend some serious savings.
Yeah, that's well said, Walker, and absolutely right. So answering kind of the why behind the what, they chose to add these components in this system. It added some weight, it added some cost. What was the gain for that? Well, for them, it was efficiency. And it is worth noting that this only applies on an all-wheel drive vehicle, right? If it had been just rear-wheel drive, then you don't have those losses. So the improvement in range would be for the all-wheel drive variant. But yeah, I mean, this is something we talk about a lot with clients, the idea of avoiding putting more kilowatt hours in the pack. They'll evaluate what is the equivalent cost in kilowatt hours that we save by having a feature, and then they're looking at that total accounting cost and going by that. So no, thank you for the math there. And yeah, it's the right way to look at it, the total system cost. So yeah, probably we would say in the ballpark of a $500 sort of savings for the vehicle by going that route. So spend some to save more, right? Good stuff. Okay, the next thing that I think we want to talk about here that was really kind of neat and novel on this whole system, and really this is unique to Hyundai and their E-GMP architecture. We're going to move over to the inverter from the rear drive unit here. And again, we're saying that between the two, they were different here, but we've got it removed from the unit here. So this, much like the Rivian we just looked at, is kind of the unit mounts sort of face down on the top of the 3-in-1 drive unit here. When you peel it back, you can see you got a few boards. So the controls, the brains of the system, you've got your power switching components on a bank under here. In this case, it was an Infineon drive MOSFET module. So MOSFET, again, we love our acronyms, but metal oxide semiconductor field effect transistor, long name that just means it's the power switching component that takes DC in your battery and switches it to AC that's going to be used in your electric motor, 3-phase AC. But looking at this, it was kind of standard fare in here. Again, we had our power switching components, our big capacitor bank. But what was unique and jumped out to us right off the bat, and say I'm putting 3 fingers, but there's 4 things here. So normally you see 3 primary leads in an inverter, and those are for the 3 phases, and those correspond with 3 leads that are in the stator. But there is an obvious 4th one here. And I know, Walker, when we first looked at that, we were scratching our heads. There was all kinds of theories on what it might be. Somehow we started to converge, I think, on the right path. But eventually, I think we found like a video, right, where they kind of described some of what the function was. And ultimately, what we came to learn was, so a key thing for this vehicle, it's an 800-volt architecture, which is, at this point, EVs are either 400 volts or 800 volts. And in a moment, maybe we'll have you speak to the virtues of 800 volts in a second here. But at a high level, the thing to know is, okay, there's a difference in the nominal voltage of the battery pack. And it's significant because the infrastructure that you might charge from, if it's only equipped for 400 volts, you have this scenario where to charge the pack at 800 volts and take advantage of your max charging speeds, you have sort of this issue where it's like a chicken or egg scenario. And the way around it to try and boost up to 800 volts, there's like kind of 3 main things you could do. One would be to add a new high voltage monument that basically works as an amplifier or a boost converter as it's known. Basically, you'd think of like a DC-DC converter. You have one in the vehicle that takes your high voltage and steps it to low to power like your low voltage system in the absence of an alternator. Think about that in the inverse where you're saying, okay, I need something that takes me from 400 volts up to 800. So you can add a new box, another aluminum enclosure that would live there, have its own cables, have water cooling. And that's something like on the Taycan, the Porsche Taycan that we saw. We've seen some other EVs in development that had that, but basically this separate high voltage monument that needs to be separately mounted, cooled, powered. That's maybe the least efficient way to do it. The other thing that you can do that we've come to learn is you could take advantage of components that you already have in your inverter, add a 4th lead, and basically use the power switching components when the vehicle's stationary, the things that you would otherwise be using to drive the vehicle. If you apply 400 volts through one of these leads, you can toggle those power switching components on and off and get a boosted voltage that will charge your battery at 800 volts. So all of that to say, essentially, what's really going on here, they added a little bit more cost into their inverter, But the power switching components are the really expensive, the tallest pole in the tent here. So they didn't have to buy another set of those. And for a little bit of cost add, they avoided putting a whole nother monument in there, right?
Yeah, because you're never going to be charging while you're also driving. So there's really no reason that you couldn't utilize existing components to achieve that function.
Yeah, it makes sense seeing it, and now it kind of seems like a no-brainer, but it's like, I mean, you have to kind of think through that, say like, okay, well, I wouldn't be using those when I'm parked and charging, so yeah, assuming no one is trying to like do like some sort of Fast and Furious thing where they're like charging a vehicle while they're driving down the highway, I think they'll be okay here. But, and I know briefly we touched on, right, this is 800 volt architecture. We were talking about this recently. Walker, what are the advantages of 800 volt architecture? Why would someone even want to do that in the first place?
Sure, so overall, there's a lot of efficiency gains to come from the increased voltage, but overall, you can reduce all your conductor size lengths, or all your conductor diameters throughout the vehicle. So all your high voltage cables can significantly be reduced in diameter, and that trickles down all the way through some of the switching components and through the stator itself. But overall, that can lead to, I think I've even seen Porsche referencing the Taycan, an 800 volt system. It can equate to tens of pounds worth of high voltage cables, which copper is not cheap. Significant hundreds of dollars of savings potentially in just high voltage cables and high voltage monuments throughout the vehicle. And then of course the weight advantages. And then on top of that, there's just efficiency benefits once you get to higher voltage, that overall it's just a more efficient system.
Yeah. Less current, less losses, less heat that you need to reject and manage. So I think we are going to see people continue to move to 800 volt architecture. In the short term, there is a little bit of a cost premium because I think the industry is not standardized on it, but I think we'll see a day where that is probably the majority of what
this is probably one of those things that kind of stands in the way, is that all the charging infrastructure is set up for 400 volts, and so 800 volt vehicles typically have had to add additional high voltage monuments to up that, but Hyundai is kind of taking a clever approach to reducing the cost burden of going to 800 volts.
Yep. And I will stress, so this only exists in the rear inverter. In the front inverter, I think I have, some of those pieces floating around here. Here we go. So what you would more typically expect to see on your primary leads would just be 3, right? So this is an example of what we maybe would have expected to see, but instead we saw the 4, which was a dead giveaway that something was going on, and basically we had to dive into it to figure out what was going on. Sticking on the inverters too, while we're talking about it here, a little bit interesting to see, right? So 2 different drive units. Again, they're both permanent magnet AC setups, but different in terms of the internal contents of the inverter, which is what drives these units. As we mentioned back here, we had a bank of MOSFETs. They were Infineon branded. These would be the most costly components in here. If I flip this over, so what you see, so this is a heat sink that's going to be used to create a tortuous path that coolant's going to flow over these pins and extract heat out of this. The way this is positioned in here, and you can see there's one sandwiched. We had that from another vehicle. They're going to flow coolant in through here, and then on the back side, it's going to be essentially bathed in coolant. And one thing, though, that we saw, and Walker, I'll kick it to you for this. I think you were the one who cut this out of here, right? Yeah. What is going on here? What is this half moon shape? Why would they do this? Yes. Why was this necessary?
So on the back side, so this is a die casting. So in order to gain the mold direction that they had to achieve on this side, they couldn't have a closed channel here. That's not really a feasible design in terms of die casting. Yeah. So what you typically see is either a cast aluminum or a stamped cover, which has to be bolted on to kind of close out this cooling channel where you see the coolants flowing through. We've seen this in the past, but recently this is kind of one of the newest vehicles we've seen utilizing friction stir welding. So we have a stamped aluminum plate, which is kind of rough now, but before it would have sat into a little groove on their casting. And then they come touch it off with a tool. You can see this friction stir welding mark that is left afterwards, but these two basically get welded together in a way where now this is a closed section, but no fasteners are required and no seals are required, because when you're doing a bolted cooling channel, you're going to have to either have liquid applied or a molded seal to close that out so you don't have any leakage. So this is a quite cost-effective means for closing out the cooling channel, because it's really not going to be a serviceable component ideally, right?
Yeah, you had to cut this off with a grinding wheel, which you would never do. But right, the point is, if you do this, you're getting rid of all these fasteners, you're getting rid of a potential leak path, the need for a seal. Basically, when we say friction stir welding, you can see the witness of this path. Think of like it's a high-speed spindle that's spinning at a high RPM. You can see they come in here, then they come, that's actually where the tool's coming off. But essentially, they're tracing this path. It's a non-additive process. So they're spinning this thing at a high rate to create friction, and they pass around this, and basically they are welding without having a stick or something else. They're just heating up the metal, and it sort of melds it together between the plate and the outer to create that leak-free path.
Yep.
So kind of clever, definitely a cost reduction, definitely something that we've encouraged others to take a look at in terms of taking cost out of not just their inverter, but other high voltage monuments. Many of them have that type of.
Yeah, we see that Kia did this on both the inverters, but as well as their ICCU, their combo charging unit. So it's definitely a technology they've chose to maximize throughout their high voltage modules.
Okay, awesome. And it was interesting to see the juxtaposition. So the cooling strategy there was the tortuous path with the pins and the cast cavity with the friction stir welded plate. If we go to the front drive unit, so the inverter was significantly smaller. It mounts on the back side of the housing here. We've got it removed. And this is not atypical here, but the power switching components were different in the front. Instead of MOSFETs, they had IGBTs, meaning insulated gate bipolar transistor. So again, another type of transistor component that's handling the switch from DC to AC. These guys, instead of being sort of a module that had cast pins, the way that they opted to cool these was to sandwich them between two layers of a plate style cooler, almost reminiscent of what you'd see as like a transmission oil cooler in like the end tank of a cooling module. Basically, these guys get sandwiched in here. There's a thermally conductive paste that would allow heat transfer between the aluminum channels and the heat generating components here. The third one goes in. I won't try and manage that stack up. But basically, once that's in there, they've got an inlet and an outlet port so that they flow coolant through there, and they're able to extract heat right at the source where they need it from. So different power switching components, different cooling strategy, multiple ways to skin the cat. Kind of neat to see them tackle a few different approaches here. Now, we were talking about cooling. I guess we should probably point out some of the highlights there. So this is a pressurized oil-cooled system. So much like any of the Teslas we've looked at, or the Rivian unit or the newer Rivian Enduro drive unit we just went through, instead of passing just ethylene glycol or coolant through, they have oil and plate-style heat exchangers that are essentially allowing heat transfer between the coolant and the oil. I guess in looking through the internals, Walker, maybe you could point out some of the internal things that they're using to actually distribute oil throughout the components?
Sure. So we could look at one of their end caps as an example, but they've chose to use these aluminum brazed tube assemblies. So you can see here, this one would mount, and this would kind of be a spray ring. So I don't know if you can zoom in and see some of these holes, but oil would be essentially passed through the housing and then reach some of these brazed tube assemblies and would spray primarily the stator conductors in this case. There didn't seem to be as much direct rotor cooling as much as stator, which does tend to be the hotter component of the two. So you can see that they're using these tube assemblies as well as some vertical brazed tube assemblies to run across the stator to spray the side of the laminates as well.
And so in that sense, similar again to what we saw in the Rivian drive unit, they are using these small orifices on here and putting pressure. This system has an oil pump, which it's very oily, so it's in a bag here for all of our benefit. But they're pressurizing the oil in there, and it's when it encounters these orifices, it's going to spray out and spray up onto these copper components in the stator, the conductor bars that are generating heat, as well as like on the end of the stator too. They're going to dribble it, they're going to spray from the inward out with that ring that Walker just showed there. So, and again, with a pressurized oil cooling system, it is a cost increase over a glycol-based system, but it's one of those instances where you pay a little bit more for a premium element, but you can get more out of the unit. So the power, the kilowatts that they're able to drive these things to, that cooling strategy certainly was a distinct choice that they made to meet the targets that they had for the vehicle. I'm trying to think, what else? I know we saw kind of an interesting component back here, Walker, that end cap with the bristles in it. If you want to maybe zoom in on that. So what are we looking at here? Why is this important?
Sure, so this interfaces with the end of their rotor shaft. And so this is going to be, so what we see here is a bunch of carbon brushes. And what that's doing is getting rid of the static discharge that could build up upon the rotor. And you would not want any arcing overall, especially with bearings nearby, that could lead to some life cycle issues. But this is one method that we've seen to do it, and what I guess we would deem as a more costly approach. In contrary, we could look at what Tesla does. So Tesla also has a mechanism to discharge on their rotor. And what they do is just a stamped tab basically that touches off the rotor. So as this is spinning, the rotor's rotating around this. This tab is just always having contact with that rotor to ensure that there's no electrical discharge going across the bearings, say. Another option, which the key happens to feature, is ceramic bearings, but we've also seen OEMs utilize ceramic bearings as opposed to either the brushes or the tab approach to handle some of that electric discharge that needs to occur on the rotor. It's interesting that Kia is kind of doing a twofold approach. They have both the brushes as well as a couple ceramic bearings throughout this.
And when we say ceramic bearings too, just to highlight, so anyone here has probably seen bearing assemblies. When we say ceramic, the actual balls within the bearing assembly, rather than being like a stainless steel or hardened steel, these are actually a ceramic, it's ceramic coated ball. So they're very, I guess, is it actually, I should ask someone, is it made of ceramic or is it just ceramic coated?
I believe they're
just ceramic because they actually are
but
super light, comparatively speaking.
This bearing is also unique in that it's kind of like a hybrid ceramic bearing, so that the cage itself is plastic, and they're utilizing a lot of plastic internals, but the bearings themselves are ceramic, and then of course the outside cages are still metallic.
So yeah, and when we talk about this, the reason you would use ceramic bearings in here is you've got ferrous element, you got a spinning rotor that goes within this bearing. You've got electromagnetic fields and a lot of power flowing through this. These isolate the rest of the gearbox from the spinning rotor assembly, right?
So you could think that this inner cage is going to be actually in contact with the rotor, and you would not want arcing across those balls from the inner cage to the outer cage.
Yeah, so potentially a means to mitigate that. Maybe belt and braces with the brushes too.
Yeah.
I was looking at this, it looks like, so that's probably the witness from those brushes being in contact, right? Because this would be on here. It's not a bearing surface, because, well, the bearing is bearing the weight of it, but it's just sort of in contact with those, and it's taking some of the static out. Very cool. Okay. And yeah, so the one thing too, and we mentioned kind of the pros and cons, there's definitely some innovative stuff going on here. The one thing that I think we were hoping to maybe not see that we did see is the parking pawl assembly. And this was something that we've talked about with other vehicles. We saw it on the Mach-E. We've seen it. It generally, like, more legacy OEMs tend to feature them, and some of the startups don't. But the whole like backstory behind a parking pawl, what it is, why it's necessary. This feature, when we say pawl, a pawl is a mechanical mechanism that's present in like a ratchet, a hand tool, right? It's got a mechanism that it will allow a ring to slip by, but it won't let it back drive. So that ratcheting mechanism is called a catch or a pawl. What they have in here, it's something that existed in all vehicles that had automatic transmissions, because you had a torque converter and you would essentially idle away if you were parked. They had that pawl in there so that the vehicle would be held stationary. That made sense in an automatic transmission, but in a BEV, you don't have that same phenomenon, right? You're not idling, you're not gonna go away. So what some people have decided to do is use their electronic parking brake system, right? And I guess what does that consist of in the rear? When we say EPB, what does that hardware look like for those vehicles?
Sure, so they already have an MGU integrated into their parking brake calipers, if you will.
So MGU, what, motor gear unit?
Yes.
Okay.
And so what they're able to do is basically, in a park scenario, they're able to physically drive and lock the calipers themselves at the rear. Typically, it's only at the rear.
Yeah.
And so it's physically parking by the calipers themselves, and this would essentially be aiding that. And ideally, this wouldn't really have much actual contact on the gear if the calipers are locked themselves, but so this is kind of a redundant system, if you will, in that way. But the calipers themselves, just by holding those parking brake calipers, could essentially act as your parking mechanism.
Yeah.
And other OEMs like Tesla have opted to solely rely on the caliper braking mechanism itself.
Yeah, and that's something we've been rooting for. Tesla was the first to feature it. Then we saw like Polestar didn't have a parking pawl, Rivian didn't have a parking pawl. We've seen vehicles get away from it. Like, I don't want to make it sound like it's a total no-brainer. You do have to mind your P's and Q's and make sure that you have the redundancy and control function and think of the different scenarios and when you're on an incline and hot disc reclamp and all that. But essentially, the old school way to make sure you're not going to roll away is to have an electrical actuator that's moving a mechanical mechanism that's physically engaging a target ring in your gearbox. Hyundai does have this. We know other OEMs that have launched with one and are in the process of taking it out. So I guess free consulting for Hyundai. This is probably $70 to $80 in cost, this whole system, and it's good amount of heft to it. It's definitely what, I don't know if we had the bag. Well, it's, I don't know, feels like it's maybe 5 pounds, let's say. But, you know, you'd love to take that out if you didn't need it, and they already have the physical hardware. It would be more of a software function that they would need to accommodate it. So we like to point out opportunity where it exists. Hyundai, Kia, maybe take a look at that parking, Paul, or give us a ring. We'll talk about it with them. But yeah, I think we've kind of hit all the high points here at a high level. I like what we're seeing, right? Definitely some innovative stuff. Definitely some things that are competitively in line. I would say that the decoupler and especially the integrated boost converter, that was probably the most unique thing about this, I would say. But yeah, looking forward to seeing more of these in the future. Walker, I think, explained most of what we're seeing here on the table to me, so thank you for coaching me up, getting me up to speed. And if anyone who's watching wants to have more conversations with a smart guy like Walker, get a hold of us. He'd be happy to walk you through it anytime. As always, thanks for tuning in. Walker, thanks for sharing it with me today, and we'll talk to you again soon.